building a permanent robotic observatories. And you would use satellites, put satellites in orbit around the moon that act as communication devices, because you cannot see the far side of the moon. So sending signals directly from here won't work, but we could send a signal to a small satellite orbiting the moon, and it can talk to the robot on the surface. So there's some interest in doing that. There's also some fringe element of optical astronomers who want to build an optical telescope on the moon, on the far side. And, they would have issues half the time, though, because the sun shines on the far side of the moon half the time, and so it would be in persistent daylight. Not ideal, but when it is in the dark, it's really dark. It's dark and cold. So anyway, you can look at the notes. I'm not going to go through all these. Some of these we covered in class. But these are here. These were from prior classes. You might remember, for example, somebody was asking me about the difference between geometry and shape. And we have this example of a torus, which is a flat geometry, but clearly not a flat shape. And in a few minutes, I'll talk about how that's relevant to what we know about the structure of the universe. Yeah, we'll see this little pop-up. Math describes a torus and a plane with the same equations. Even though the torus has a finite surface area, and this plane, both have the same geometry, but the plane is infinite in extent mathematically, and the torus is not. This is this mind-bending stuff that bends. Well, actually, here's a little bit more about it. And I've done this in class a few times. You take a flat sheet and roll it. This is still flat geometrically. And if you bend it, there's some argument about this, but if you bend it like this, and you get the donut shape, clearly not a flat shape, but a flat geometry. And then you have Escher, who confuses us by showing how you draw ants on a Möbius strip. They travel for their whole lives and never get, there's no end. This is useful to think about, because people often have the misconception that the universe is inside of something. It is not. We are on the surface of something that we could only visualize if we had one higher dimension to work with. I think there's an example here. And then this is called a Klein bottle. So if you walk on the surface of the Klein bottle, you will go into the bottle, you go into the mouth, or start in the mouth, and you go, now I'm showing you, you're inside of this part. Right? So you can come around here, but then you can go to the outside, and you never you never have to cross a boundary. And then this is what, if you go to the next higher dimension and do this same thing that's illustrated here, from flat to cylindrical to a torus, if you do that with a cube, you can end up with what is called a two-torus. There's a small community of mathematicians who study these things and understand higher geometries, higher dimensional geometries. And Joseph Silk, I'll remind you about Joseph Silk. He either is or was recently the Astronomer Royal, that is, he was the Queen's astronomer in England. Very accomplished guy, and I'm not going to read this to you except one little part of it. But this dates back, most of this page dates back to 2001, where he was interviewed about the geometry of the universe, and he said, he was actually asked, is the universe infinite or finite? And he said, we don't know. And then I highlighted in red, he said, if the universe is finite, then it's a two-dimensional geometry, something like a torus. So now we're well into the issue of what are the unresolved questions in cosmology. The actual geometry of the universe, we think, is flat, but the shape is open to dispute. And is the universe finite or infinite in size? We don't know. So you should just know. Now, oh, and by the way, down here there's a link right here on the bottom line. Well, if you click on that, this is a recent interview with Joseph Silk. So now 18 years have gone by since this occurred. This little link here is another conversation. Joseph Silk published a paper in November or December of last year, disputing the idea that our geometry is flat. Yes, sir.
Why would he say a torus instead of just a sphere? Which is simpler.
Yeah, I don't know. There's some other discussion in here, in this page, where he's stumped by this question. Is the universe finite or infinite? A sphere is a possible solution. It has to be a surface that has no edge. So remember, we many times in our meetings talked about ants on a sphere having a two-dimensional experience. Their cosmology is one defined by a finite surface that they're confined to. They don't know about up or down. They just know they can go forward, backward, left, or right. And there's no edge to their universe. And it's a finite size. And if it happens to be an expanding universe, they will see their neighbors move away from them. That's the experience we're having. We see galaxies moving away from us. But that's not enough to define what is the shape. It's a dilemma. Here's what Brian Greene says. There's a lot of words here too. And he highlights this in bold. I think you can probably read this from where you're sitting. So the three-dimensional spherical surface of a balloon in a four-dimensional space is an acceptable shape. So Anselm's right. And this is the same book in which he says, when the professionals have a conversation on this topic, they stop using words. They start writing equations, because in the mathematics you can conceive of what's called a three-sphere. It looks like a beach ball, except it takes three dimensions to describe a point on the surface of this special kind of sphere. And there's an infinite number of higher dimensional spheres. And the universe is perhaps describable that way. So this is an unresolved issue. That was the point of this meeting today, is unresolved issues. Now, some of the questions that are currently unresolvable, I put in a category that they're within reach. That if we do make more measurements and we keep funding people to do theory, we'll figure it out. And cosmic rays is one of those. We've talked about that in here, that these very energetic form of electromagnetic radiation that's bombarding the atmosphere and produces showers of fractions or parts of atoms. Where are the cosmic rays coming from? Right now we don't know, but if we keep observing, we'll figure this out. The possibilities are they were created when the universe was born, and they've just been flying around waiting for an atmosphere to hit. Or there's some physical object in the universe now that's producing them, but they are unbelievably powerful. One of them was like, what is it? There's a rare form of cosmic rays that has the energy of a baseball going 30 miles an hour. This is an invisibly tiny chunk of light, so powerful that if you were wearing a baseball glove, you would feel it hit you. I mean, most of what astronomy does involves microscopic amounts of energy. I saw when I was a student, here's a metric for you. When I was a student, radio astronomy had been around for 30 or 40 years. And a kind of rule of thumb was the totality of all the energy collected by radio telescopes from the time of their invention in the 1930s until my time in school in the 1960s, was the same as the energy involved in the ash of a cigarette falling into an ashtray. It's almost nothing. And so we're surrounded by cosmic rays. We don't know where they're coming from, but I put this in the category of we can figure this out. What are the mechanisms that are involved in supernova explosions, where a massive star finally undergoes some process that we don't understand exactly? It collapses, an enormous, stupendous amount of energy is released. And what's left behind sometimes is a black hole, and sometimes is a neutron star. We're going to talk about neutron stars more this morning. But that's a solvable problem, this idea of what goes on in a supernova event. In fact, there was news yesterday on this topic. Yes, sir?
What's the difference between a neutron star and a dwarf star?
Well, neutron star is a dwarf star. I mean, there are what are called quasi-stellar objects. A neutron star, a white dwarf, black hole, there's a collection of these things. They're the residue of a collapse of a larger conventional star that radiates. But like a neutron star, very interesting what goes on there. So I'll just take a minute on this. You know, atoms are made of nuclear particles, protons and neutrons in the nucleus of an atom, and electrons. If you have enough mass, the pressure is so intense that the electrons that are orbiting around in a cloud around the nucleus, those get forced into the nucleus, and they neutralize the protons. The proton has to allow the neutron, the electron into its home, and the proton is positive charge and the electron negative charge, and they're crushed together by this enormous pressure, and you get neutrons. And there's already neutrons in atoms, so now we have nothing but neutrons, and that's called a neutron star. And a neutron star with twice the mass of our sun is about the size of Central Park in New York City. Just a tiny little thing. And there are some of them that are very special. We'll talk about this. Okay, so we will eventually understand supernovas. Do black holes have internal structure? This is an area of very active research. That is, there are real tensions in understanding the intersection of conventional physics and black hole physics. It has to do with the topic of information. If you throw an encyclopedia into a black hole, is the information gone? Physics, conventional physics says the information is never destroyed. Black hole doesn't want to give that stuff back, though. It's black. Things that go in never come out, except maybe. And this is where Stephen Hawking is involved. So if you're interested in this, a very intriguing topic, it's been around for 30 years, it's unresolved. Leonard Susskind has written a book about this for the public, if you're interested in that topic. That will work that out. Fast radio bursts, we talked about this, was that last time? Mm-hmm. This note about we'll figure out fast radio bursts dates back several years when I wrote this first version of this chart. We're beginning to understand fast radio bursts. Remember, I was talking last time about this. There's a spot in a galaxy 500 million light years away that turns on and it's active with fast radio bursts for 14 days, and then it gets quiet. And then it comes back on for 14 days, and then it's quiet. We don't know why that's happening, but this is within reach. As you might expect, the right-hand side here, I'm going to show you the ones that I don't know if we'll ever solve. So, what came first? Galaxies, all of which have black holes in their center. Or which came first? The galaxy and the black hole was the product of the galaxy? Or was the black hole first and then the galaxy formed around it? This is I think, a solvable problem. the more observations we make and the more gravitational wave sensors we build, the more evidence we'll have to chew on to kind of understand this. Here's what I would say to you, that if you go back in time 35 years and enter this classroom, and somebody like me was giving a talk on cosmology at that time, the list of things that were unresolved would be enormous. So much progress has been made in the last 35 years because of new observatories and more people working on the theory. We actually understand some stuff now. Like 35 years ago, the concept of the early universe and the idea of inflation as a way to explain what we observe in the universe today, that did not exist. That's a 30-year-old thing. Alan Guth, 35 years ago, maybe he had an inkling of an idea. But so many problems have been solved. So I'm hoping this list will get shorter in one way. These will not be the problems 35 years from now. Some of these will be solved, but there'll be more new problems. Okay, now deeper questions. I talked about this last time. Why is the dark energy that we observe in the universe it's so important, and yet if you had a box of it in front of you and you made measurements of its properties, you'd say, why is it so small? Why is it? Because we go in the lab and try to measure the equivalent of dark energy that you can create in a laboratory or conjure up in a theory. The best estimates we have are dramatically different from what we observe in the behavior of galaxies and the expansion of the universe. This is a very deep mystery. I don't know. Maybe somebody will figure it out. We're going to talk about this, the Hubble constant. We have different techniques, and this lecture got modified last night because there was stuff in the news yesterday on why we can't figure out the Hubble constant. Using different techniques, why aren't we all getting the same answer? There's like 6 different methods now, and they all group into 3 different answers. The whole of astronomy or astrophysics is on fire about this topic. They cannot figure out what is it that we're missing, which is great. This one, was the universe tuned so we could be here? I'll have more to say about that. This is also a deep question. Can we ever expect to detect extraterrestrial life? So as I said, we have found lots of planets, and there's a handful of them that are like Earth. That is, they're in what we call the Goldilocks zone. They're not too hot, they're not too cold, they're just right. And they have water. This is all, egocentric thinking that we have to, whatever life we find, if it's intelligent life, it has to be like us, based on carbon, based on water, and liquid water. Not, could life evolve on a frozen, persistently frozen, icy planet? Astrobiology is attacking this problem. Here's the issue, though. Anybody we find is going to be far away, way far away. Even in the galaxy, if there's life in the galaxy, and later this morning you guys are going to calculate how much life there is in the galaxy. It's 200,000 light years across the galaxy. So if you send a signal, even if it's a nearby neighbor, 1,000 light years, you send a signal out, that let's say I'm highly suspicious that that star right there has a planet that has life on it, I'm going to send a signal in that direction. It will take 1,000 years for your signal to get there. And you could ask them, how are things? Send us a photo. And it'd take 1,000 years for them to send for their message. If they respond immediately, they'll send a message back. One of the pioneers of quantum mechanics, Pauli or Fermi or one of those guys, has a paradox named after him. He said, it seems like there's a lot of stars. And he didn't know it at the time, but every star has planets. This is what we're finding from the survey satellites that we're looking at. Every star has planets. Some have many planets. There's a gazillions of planets. If life can form on Earth, why couldn't it form on one of those planets? And if they are intrepid travelers, why haven't we heard from them? Where are they? That was his question. So there are a couple of possibilities. One, we're the only ones that have technology. Two, they don't care. They know we're here and they don't care. Three, they know we're here and they're not making any noise. They just don't want to be bothered. They don't want to be exposed to the alien life forms that might be in the galaxy, because they have been through this. Maybe they're old societies that have been through many catastrophes, and they know coming in contact with other life forms is dangerous. There's a lot of answers. So that'll be a question for a long time. Are there an infinite number of universes? This is something that's in the press all the time. Once again, it's something the metaphysical community grabs a hold of, and they are excited about speculating about infinite number of universes and what that could mean, what it means for life after death and so forth. But there are serious scientists who are absolutely convinced that this is not the only universe. I don't mean that this is not the only volume of space. I mean, they're talking about coexisting universes that we cannot see because the dimensions they exist in are not accessible to us. One clue, which a few people, ironically women, there are women astrophysicists have collected around this one thing. It has to do with gravity. I've talked about this before. There's 4 forces that physics knows about. The strong force, which keeps the nucleus of atoms together, even though they'd like to fly apart. The weak force, which participates in radioactive decay. The electromagnetic force, which is responsible for all the light in the room and our technology that we use in our society. Those 3 forces are kind of grouped together in terms of their strength. And then there's one other, gravity, and it's dramatically different. It's very, very weak compared to, do it this way. How much matter does it take to produce a certain amount of force using electromagnetics, the strong force, the weak force? And it's kind of like the same amount of matter. It takes an enormous amount of matter for gravity to exert a force. Gravity is now going, I'm going to let go of this eraser, and gravity is going to act on it. And it accelerates. It takes the entire planet to make that happen. The entire globe of Earth to make this thing do that. You could do this trivially with electrostatics, with almost nothing, a little 9-volt battery. You could make this, you could suspend this object against the force of gravity. So a little tiny 9-volt battery that we all are familiar with could overcome the influence of all the planet, all the matter in our planet. So this group, it's accidental, I think. There's 3 or 4 women who independently are working on this idea that gravity is a manifestation of a force that is strong, but it's in another universe, and we see it as weak because it just kind of sticking its finger through the wall. And I'll have more to say about that. Where's all the antimatter? We have a really good model of the early universe. It predicts the amount of material in the universe very accurately. It predicts the amount of hydrogen, helium, lithium, boron, bismuth, all that stuff. And then astronomers go out and measure how much is out there. And the theory is really good. But the theory also